Laminated composites can be unidirectional, bidirectional, or angle plies. One may also want to model a combination of these three in what is called a multi-layered composite. In this video, I will show you how to model multi-layer composites beginning from the theory behind their design, the creation of their virtual domain in ABAQUS, and also simulation of the uniaxial and shear deformations. So let's sit back and relax as we get started with this modeling. Hello, welcome to CM Videos. My name is Dr. Michael Okri. So the outline that we're going to work with in this video is that we're going to show you the theory behind multi-layer composites and setting up of the model within ABAQUS so that at least you get a sense of how to do this for yourself. And then we'll show the analysis of the simulation of the results generated from this, and finally show you also how to generate stress strain graphs and effective properties from this type of composites. So let's think about the virtual domain that we're going to create. So this is a written volume element of a multi-layered composite. It's a cubic RV with length, width, and height specified, and the fiber diameter we're looking for here is a 5 micron diameter. It's going to be a 2D6. So the stacking sequence that we're going to be modeling here would be a 0, 45, plus 45, minus 45, and a 90-degree stacking sequence. It's not necessarily symmetric, but we just want to show the possibility of modeling different angular orientations. So to look more closely on that, so the stacking sequence has been defined, and that's really depending on the orientation of the different lamina of the material. So here we've shown different fiber arrangements, and when you mix it together with the metrics, you get this arrangement. And just by way of associating each lamina to the fiber orientation, so we've got the 0 degrees at the base here, a plus 45 degree here, and that's minus 45 degree here, and a 90-degree orientation. So this is with respect to the main fiber axis, which is a 0 degree direction. So how do we arrange the fibers, if you would want to know? So basically, we think about the units. So typically you have a volume fraction that you want to achieve, and that volume fraction is therefore related to the fiber packing fractions and also the diameter of the fiber. So this is a unit cell for the system that I'm going to be looking at here. So it's sort of a square unit cell with fibers oriented at the four corners of this square RVE, and the typical dimension I will be working with is 7.5, 7.5, obviously based on a diameter of 5 microns. So we can use this volume fraction relationship. In this case, there's only one fiber because you see there are 4 fibers here. So if you cut 1/4 of them, so you end up leading to 1 fiber. So what I've got here is just 1 fiber pi this to the power 4 divided by 4 LD. So that gives me a volume fraction of 35%. So if you want to try and model a different volume fraction of this, then you can either change the length and width that is defined in this case, keeping the fiber diameter the same and the volume fraction changing. So it really depends on what you want to do. So the way I'm going to do this in terms of the RV of the multi-layer composite that we're going to work with will basically look like this. So I'll create it first in this way, and then later on we can now section it to create the fiber, the multi-layer system that we're looking at. So basically we've got 4 laminas that are oriented according to the stacking sequence, with this being the 0, plus 45, minus 45, and a 90-degree orientation. If this is the kind of content that you like, please, I do encourage you to subscribe to this YouTube channel, so when contents like this are made, you'll be the first to see it. I also want to highlight that there is a CM Videos Insider group, which I regularly send every week. Newsletters talk about behind the scene in CM Videos and more about products that's available on CM Videos, and also offer my perspective on a lot of computational modeling issues. If you're interested in these kind of things, please do subscribe to this CM Videos Insider group. All right, so in terms of the material properties that we're going to be using for this, so the material properties here would be metrics of these properties and the fiber of that properties. So what else I want to really see is that the metrics would have a post-yield strain softening associated with it, and this will be the kind of strain softening we'll see with this metrics. So all that information will be incorporated in the model as we begin to model it. Now the case study that we're going to be looking at first here is a tensile deformation along the fiber axis of X, which is this X axis, and then also there will be a shear axis deformation which is along the YZ plane as shown here. So just a quick question of the day: what is the stacking sequence of the multi-layer composite that you are interested in modeling? Clearly in this case I'm looking at a 0, plus 45, minus 45, and a 90-degree. It's possible you want to model it differently, so do tell me in this comment section what exact stacking sequence that you are really working with, and then that could be inspiration for me to make maybe another video dealing exactly with your kind of stacking sequence. So we're going to go straight into ABAQUS and begin this modeling. Okay, so here we are in ABAQUS, so we're going to just go ahead and begin the modeling. So we start with a lamina, and it's going to be extruded and all that will be accepted. So we'll draw the fiber. It's a central fiber with a diameter of a radius of 2.5. We'll pattern that so that we only have a separation of 7.5 according to the units that we indicated at the beginning. So that's that. So we pattern it again, but this time around we're going to flip it so that we've got a central system. Click done, and then the depth is, so let's use a depth of 50. So that's one of the fibers. So we'll go to this one of the lamina. So this is the first lamina, so we need to create more lamina too. So the second lamina, a third lamina, and a fourth one. Okay, so then we have to translate. So we basically select the second lamina in the group, and we need to translate it from the origin up to a y distance. So we're going to move in the y direction of 7.5 because we want a unit cell of 7.5 as shown here. And then we'll now move on to the next one, the third category, and 7.5 times 2 from the origin. So it starts from the start point, and then the origin here will be 15. Okay, and then we'll do the final one. So this will be 7.5 times 3 from the origin and up to a distance of 22.5. So this is what gives us the distances. So we've got all the fibers oriented just like our sketch initially showed, but clearly what we need to do is to rotate some of them, plus 45 minus 45 and then plus 90. So we're going to use the middle region here to define the center, because we want to rotate about the center, not about that end. So we'll click and hold and then switch to this one, which is a created atom by midsection. So this is the middle one, so we select that point and then we need to rotate it so that we can find also the central point there, which is here. So that gives us a datum point right in the center line, which we are going to use for our rotation. And then the next thing that we need to also create a reference frame that we're going to rotate about. So we're going to call it our reference CYS, CSYS. Okay, so select the coordinates. So we're going to use this as our reference. We want to select a specific point which is indicated, so we now have that as our system. So then we can now rotate. So what we're going to do, select the instance. So select the instance to rotate. So we want this middle one, and we want it to be rotated about this axis, the y direction, and 45 will be fine. So we're happy with that. Select that, select the instance to rotate, which is this, and we want it rotated about that axis and minus 45. Okay, so we have it looking like we expect, and then the final one is to select that, and that's still rotated about that axis, but this time it's 90 degrees. So we now have the arrangement of the fibers as we want them, everything perfectly arranged. So we're going to create a matrix as well. So a matrix would take all those structures as well. So what we're going to do with the matrix is that we're going to probably make it 0, 0, and we want it 45, 30. Okay, and then we want it as deep as 45 as well. So this is our, so create it as matrix system here. Okay, so that looks about right. Okay, so what we're going to do is to move it so that it lines up properly. So I'm going to select it from here, starting from this corner until it gets to that corner. Okay, so we now have a perfectly arranged system in that axis, which looks alright. So click OK. So we could go back and just make it line up with what we had before. So our metric system, the depth of extrusion, we want that depth to be 50 so that it lines up with what the fibers were initially. Okay, so go back to assembly. So it does look like it's lined up with the length of the fiber. So everything looks alright as we would expect it to be. So what we can then do is to start trimming, but before we need to trim, so we need to match cut. So this will be mesh code, so I'm going to call this LVE of the multi-layer composite. So we return the intersections, and then we need to select everything at once and click done. So this is fine. So what we'll notice here is that we now have a third part, which is the part for the multi-layer composite. So now we've got the multi-layer composite. So obviously we want to go into trimming, so we'll click on that to trim. So I'm going to select maybe this plane for now. And okay, so what do we do with that? So clearly we want to trim this to that point. So we select from here to that point and then get a bigger one to fill it up. So and then extrude through. So that looks alright on that plane. Okay, so that looks alright on that plane. So we could try another trimming on this face as well. So we could say, okay, fine, select that vertical point and then trim as well. Let's say from there to there, and then just to get the edges out. So we'll run across. So we've got a structure, but clearly because of the plus 45 minus 45 degree on these faces, it doesn't look as we'll expect. So what we're going to do now is that we're going to try and create a sketch on this plane that we're going to use. So we'll select this, and let's select one of these and then clear the edge. So that looks like that. So what I'm going to do is I'm going to put some construction lines just to indicate where the center of the structure is. So I'll put those construction lines. So we're going to put the construction line right in the center of the structure and another one right in the horizontal section. So I'm going to use them as reference, but I need to fix them. So I'll select that, click fixed, and I select this, click fixed. Right. So what we're going to then do is to just randomly introduce some vertical construction lines. Vertical here, vertical there, and then maybe some horizontal ones as well. Horizontal there, horizontal here. So but then we need to make sure that we have the right distances apart. So I'm going to have to dimension between here and that vertical line. So it should be 13.75 to give you the distances we are working with. So let's use 13.75, and then we'll do the same thing from here to there. So that's 13.75. Okay, so this is the distance, so we'll make sure that distance is fine, and then we'll do the same for the vertical part. So 13.75, and the same thing from here to there, 13.75. The idea here is that we want to then create a structure that is quite nice around this region. Okay, structure that is perfect in every sense, so that it will be the center line that we're going to work with. So what we then will do is, okay, we'll start off from that corner and then find where it meets on this other corner. So this is fine. Okay, and then we'll get a bigger one. So this way we're ensuring that the structure that we have is a perfect structure across in every sense. Alright, so we now have a perfect LVE system. So this is excellent. So we've got all the fibers, we've got everything in the right window. So we now think about the materials that we want. So the first thing is E-glass. So the E-glass would have essentially an elastic property, which would be 73.9 and 0.2, and we'll look about the matrix, which will be polypropylene. We'll have an elastic property of 1.308 and 0.40. Then we've got a set of plasticity properties. So now we're going to create the sections that we need for this. So the sections would be first fiber section, and then the polypropylene section. So we'll go ahead and do a section assignment. So double click here. So we're going to select only the matrix, which is that, and make it PP, and then still select everything, press down shift, control, press down control, deselect the matrix, leaving behind only the fiber, and then that becomes the fiber section. Okay, so we just make sure that it's properly selected, so that gives you that the materials and the matrices are properly selected. So we can then do the meshing. So at the moment 1.4 is recommended, so we'll accept that, and I'll probably use a tetrahedron for that. Okay, so that gives us the mesh domain. So the first set we'll need to do here is X front set, and I'm going to use nodal set to select it. So I'll change this to biangle, hover in the front set, so that select the set of nodes in the front. So Y top set by node as well, so select the top, it's done, and then we'll do it for all the remaining parts. So we've got all the sets selected as properly and everything looks good. So the next thing we need to do is to find a reference point on the corner where we're going to apply our load. So what we're going to do now is to query. So if I query this point here, okay, and basically this is what I need, so I'll copy that point and then create a reference point on the, so I need to switch to parts, so to reference point, so I'll paste it in here, but I can make this maybe 18. Alright, so we've got our reference point. Then we need to create a reference point set for that. So reference point set, which will be attached to this. Okay, so this is done in the path module. So we've got everything in the path module. So create a step. So I'm going to call this a loading step, and it's a static general loading step. So create the history output. So reference point history output, and this will be attached to the reference point set, and RF1 reaction forces and displacement. Okay, then we apply our boundary conditions. So this will be X, it's an initial boundary condition, and then we attach it with the back, fix it in one direction. Okay, then Y, so that's it with Y base, fix it in the two direction, Z roller, and then we'll fix it in the third axis. So we've got the model looking the way, then we'll apply a load. So this will be associated with a loading step, and this will be attached to the reference point and in the X direction, so we could do 6. Okay, so this is a tensile pull, and then we need to link it using a constraint equation. So constraint equation, and basically with our constraint equation what we're looking to achieve is 1 X front, 1 degree of freedom, which is the X axis linked to the reference point, and a -1. So this is how you make a connection between this front and the back, so that when load applied, this is what you're going to get deformation in the correct way. So this is everything we need to set up this first model, so we can rename it. So this will be multi-layer composite extends. Okay, the first one, so we can copy this and create a second one, is shear. Okay, so with the YZ shear, we'll go in here. So YZ, so that means we're applying our load in the Z axis. So I'll take that load from 1 and apply on the Z axis, and I'm going to make it a minus so that it can push backwards. So basically we're linking this to that, and we change the constraint equation so that it goes to the Y top, but it's in the third axis, so that is Y, Z, third axis. So now we're linking this behavior to that point, so it's pushing backwards and making that connection. So the other thing we need to do, the Y base would obviously change to a fixed boundary condition. So this will be an F. So if we open the Y base, we need to fix it in all three directions. Then those two have to be suppressed because they are not active, and then we'll create one more, which will be the Y top. So it will be an initial boundary condition. So the Y top. Now it will be fixed in the Y direction because we are moving freely in the Z axis. So we can create our jobs. So we'll submit the job and then we'll look at the results. So this is the X tensile deformation, and if we just animate it so you can see what's happening. So the fiber right at the top here is taking a lot of the loading as you pull in this direction because it's the main fiber are oriented in along that direction, so it's taking all the loading here, and there are a lot of things going on here. But if we just stop this and switch it to the plasticity, so we can see clearly what is going on. So clearly the fibers are taking the loads, the plus or minus degree 45-degree fibers are right here, and there's also the 90-degree or the 0-degree fiber in this direction. So if we keep looking at it so you can see what's happening, so the loading is, and the fibers are moving, the fibers are orienting the way they should be. So this is sort of what you get. So just to probe a little bit more, so let's switch back to the von Mises stress, and what we're going to do is to hide. So if we select and remove selected, so I'm going to say based on material, then we can select the matrix and remove the matrix, so leaving behind the fiber. So you can see what's going on here. So the 0-degree fiber is taking all the loading like we expect, and the other ones are not. And then there's a little bit of rotation for the 45-degree fibers, mainly undergoing a shear deformation. So if we look at the shear deformation, if you can see the predominance of shear in the plus or minus 45 degrees as they keep rotating. So we can look at all possible angles, possible shear deformation, which is what we expect. So they would take a lot of shear deformation as the body continues to rotate under the uniaxial load that is applied onto them. Okay, so this is sort of what we'll see here. So if we flip it around, invert the display, then we can see the matrix, and then it gives us a picture of what's happening with the matrix, beginning from the von Mises stress. So again, the matrix undergoing deformation, and we can see clearly how the deformation is going in one direction, which is the X direction of loading, and so on. So we'll bring back everything, and in the one direction there's a clear dominant deformation in dominant loading of the fiber in that axis. If we load on the other axis, this one's at the base would be the dominant deformation mode. So let's look at the shear case. So with the shear mode, we see a similar kind of deformation with the body deforming in that kind of axis in shear in von Mises style. So if we switch to, so this is shear deformation and the YZ plane, the 2-3 stress, which is what we simulated, and then we get that result. So let's look a little bit more closely on the plasticity. So with the plasticity, so you clearly see what's going on here. So the fibers are anchored and fixed securely at the base as we wanted, and then the top is deforming. So you get clear regions of deformation at that point. So this is what you see, and then you get some interesting shear associated with the shear deformation. Okay, and what happens if you look inside more? So let's go back to the von Mises stress, and then let's take away the fiber. So based on material, so take away the matrix, so leaving behind the fiber, and then we can see, so you can see there's a clear sliding of these fibers, so creating this strong region where there is a plastic deformation, significant plastic deformation, because that's what we saw. So there was a significant plastic deformation at this base, as we saw that previously. So if we invert it, then it will clearly show us what's happening here. So as the structure deforms, there's a clear region where there's a lot of plasticity going on in the material, and that leads to eventual failure on that plane. So that's the shear stress deformation. So if you're looking to extract the stress and strain data as well as effective properties from this kind of simulation, so you need to look at this video, which is for a UV case, or this other video for a bidirectional case.